Okay, so repetition from the last two lectures. We discussed the dynamic problem and the response of a single degree freedom system. You remember this diagram, which shows the amplification factor on the y-axis and the frequency ratio between the forcing frequency and the structure frequency on the x-axis. And as you remember, we said that when they are close to each other, we have the phenomenon of resonance. And where this happens, it depends on how much damping we have in the system. The more damping, the more the peak will shift to the left. And then we also said that if we are in this region, we don't really have any dynamic problem. So up to 0.25, 0.3, the frequency ratio, the dynamic factor is 1, which means that the static displacement and the dynamic displacements are more or less the same. And we have what we call a quasi-static problem. So we don't need to consider the forces coming from the inertia and also from the damping. We looked at one of the powerful methods for solving dynamic problem, and that is the modal analysis or mode superposition analysis, which say that we can create a response by summing up the contributions from the different modes. So U is the total response, Q is the generalized coordinates, which is a time function, and theta is the model is the mode shapes or the model matrix, if you put it in a matrix form. And then one way of doing this is to uncouple the equation of motion. And the way of doing this is taking a pre-multiplying and a post-multiplying with the mode shape n. And due to the orthogonality properties of the mode shapes, always if you take multiplication of two different mode shapes, it will give a zero number. And if you give the same, it will not be a zero number. So in this case, if it's the same, it will give what we call here is the modal mass. If it's the same, the modal stiffness, and here there will be the modal force. And if it's different, the contribution would be zero. By doing this manipulation, we have uncoupled the equation from a matrix into equations, simple equations like this form, with the modal mass, modal stiffness, and modal force. So instead of solving this, we can solve few of this and calculate the contribution. So one way of solving this in the modal analysis is to, for each mode shape, for example, and each mode frequency, for example, omega n, we can calculate a dynamic factor. And then we can calculate the modal amplitude by simply taking the static, which is the modal force divided with the modal stiffness, and magnify this with the dynamic factor for this mode. And then when we have calculated QNs, for each mode we want to include, we multiply it with the corresponding mode shape, we add to the second and the third and so on, and then we get the total dynamic response. So this is the idea of using the modal analysis. Normally we don't need to consider more than the first few mode shapes and frequencies. Last week's lecture, Ignacio Gonzalez presented time integration methods, and mainly two types of methods, the explicit method and the implicit method. The explicit method, for example, the central difference, the implicit, for example, the average acceleration. The main difference between these, as you can see here, is that in the explicit method, to calculate the response at the next time step, this is a function of only what's happening in previous time steps, okay? Compare this to the average acceleration method, the implicit method. What's happening in the next time step is not only a function of what has happened, but also what's happening in the time step, in the next time step. So you see u, I plus 1 is a function of the velocity at I+1 and the acceleration at I+1, which make this a bit more complicated to implement. It's more difficult to program, but there are, of course, advantages and disadvantages with both methods. The explicit method is very simple to implement, to program. It requires very small time steps. On the other hand, it will have some convergence problems if you don't fulfill the requirement for the time step. So it can be unstable, as we'll see from the next picture. Implicit methods, they are always unconditionally stable, so they will not show the same instability in the response in the analysis. On the other hand, it doesn't mean that if they are accurate. We still have to have a small time step to get an accurate result. You see here, for example, the stability problem. I'm not sure if Ignacio showed this, but for the average acceleration, as I said, is unconditionally stable, which means that the procedure that is always converges, but it doesn't mean that it will be accurate enough. The central difference needs some criteria on the delta t. As you see here, the delta t is the period for that highest mode shape you want to include, divided with the pi. And for example, if we take a case when we want to include frequencies up to 4 Hertz. So 4 Hertz means a circular frequency of 8 pi. This means that we'll have delta t equal to 1 divided with 4 divided with 3.14 pi. And this will give us a delta t which should be less than 0.0796. And if we have a look at, for example, two different delta t's, 0.01 and 0.07, both of them are less than this, and we solve for the central difference approximation, we see that we get quite a good agreement. So by doing the analysis for these two time steps, we can find that the response is more or less the same, which we can then make a conclusion that the delta t is enough. On the other hand, if we just increase the delta t from 0.07 to 0.08, which is a tiny difference from this one, we will get a crazy unstable solution. Now, if we are analyzing this and we haven't checked several time steps, we look at this and we can be cheated and think that, well, this is a correct solution and we have a resonance problem. But the problem is not a resonance problem. The problem is that we don't have small enough delta t. So this is a danger when we are using explicit methods like the central difference. So you have to be careful. So what I recommend you to do is that to test always when you do the solution, test at different delta t's just to make sure that you have a solution which converges. Okay. All right, so to summarize, single degree of freedom system, we can solve this with the Duhamel integrals. Actually, no one is using the Duhamel integrals now. It's old-fashioned way. Today, we use, for example, the multi-degree freedom systems. We can use mode superposition, dynamic factor. We analyze mode shape by mode shape. Including the mode shape and the dynamic factor for it. But we can also use direct integration methods, which was the lecture by Ignacio. Here we can choose explicit or implicit. And there is, as I said, advantages and disadvantages with both of these methods. In majority of our cases, we use the implicit methods. The explicit methods can be used when we have a very short time duration loading. For example, if we have explosion loadings, impact loadings, cracking in material due to loadings, then we use explicit methods if we want to analyze dynamics of that. Okay, so that's just a quick summary of previous lectures. I will stop the recording now.